Hello friends, so in this week we will cover the indoor air quality guidelines and methods for their control. So first we will have an introduction. The indoor air quality guidelines are provided by several international agencies. So in addition to guidelines, they also have standards for indoor air quality. Such agencies are the World Health Organization, WHO, the Occupational Safety and Health Administration, OSHA, the Environmental Protection Agency, EPA, the Centers for Disease Control and Prevention, CDC, and the American Society of Heating, Refrigeration and Air Conditioning Engineers, ASHRAE. So the World Health Organization actually works on developing, maintaining the health of the entire world. That is its mandate in a way. For air quality, it works on developing health-based guidelines for maintaining air quality with a view to controlling the impacts on human health. The WHO was founded in 1948 and is an organization for 194 member states. It is headquartered in Geneva, which is in Switzerland, and has 6 regional offices and 150 field offices across the whole world. The OSHA, Occupational Safety and Health Administration. So as the name suggests, it basically deals with occupational safety and health. So the OSHA sets workplace standards, including those related to indoor air quality. So it makes standards for the overall health and safety in the occupational setting, meaning in factories or other industries where people go to work as part of their occupation. So in the purview of all the standards and quality, we also have the indoor air quality, which is set by the OSHA. So it's basically governed, or the driving force is the Occupational Safety and Health Act of 1970 in the US, to assure safe and healthy working conditions for all the workers, and by authorizing the enforcement of standards developed under the Act. Then there is the EPA, US EPA. So first we are looking at global and other countries, and we will also have for the Indian scenario. So EPA's indoor air quality guidelines cover various aspects of indoor air quality. These include maintaining or mitigation or keeping a check on health risk, then exposure reduction, so reducing the exposure to different kinds of pollutants in the indoor air environment, which basically will in turn reduce the health risk. And then how can the air quality be improved in the indoor environment? It also provides an indoor air quality reference manual and a building air quality guide. So it even provides guidance to people who are constructing or designing a new building on how to go about the construction and whole arrangement to have a appropriate indoor air quality. Then we have the International Organization for Standardization, ISO. ISO also provides a framework for assessing and improving the indoor air quality in buildings. So we have actually looked at this before in one of the earlier weeks. So ISO provides these guidelines. It also addresses many factors that will affect the health and well-being of the building occupants. So it contains a whole suite of factors and scenarios to improve the overall health conditions. There are other agencies such as the Centers for Disease Control and Prevention, and it also provides guidelines for maintaining clean air in buildings with the view of preventing any spread of disease. Preventing spread of disease as well as controlling or preventing disease from happening. Finally, there is this American Society of Heating, Refrigeration and Air Conditioning Engineers, and the idea here is that it develops standards for the air systems and also the air ventilation systems and the indoor air quality. So what is a guideline and what is a guideline value? So guideline is a sort of recommendation or a guidance given on the protection of human beings or receptors in the environment from adverse effects or pollutants. So guideline can be more qualitative, that one should do something, one should not do something. Whereas a guideline value is a particular form of guideline. It has a numerical value expressed either as a concentration in ambient air or as a deposition level that is allowed. So guideline value actually gives a hard number, a quantitative information on what can actually be done or achieved to enforce this guideline, whereas guideline is more like qualitative. Okay, like the concentration should be controlled, that is a guideline. The concentration should be controlled so that they are below 1 microgram per meter cube. Now we have a guideline value 1 microgram per meter cube. So that is the difference. Standards. So there are now standards in air pollution. Standards basically is the level of an air pollutant, such as again a concentration or a deposition value, that is accepted by a regulatory authority as enforceable, which means the agency can force an industry or a building person or a building management or anyone to make them comply with this standard value. It is enforceable by law. It can also contain measurement strategy, data handling procedures and uses statistics to derive the value to be compared with the standard. So the first edition of WHO air quality guidelines, they were published in 1987 for Europe and included 12 organic substances, of which 11 were gases and polycyclic aromatic hydrocarbon. There were 16 inorganic substances, of which there were 6 gases, 8 metals, asbestos and particulate matter as PM10 and total suspended particles. And then it also included an annex specially for the tobacco smoke. This guideline was then updated in 2005. So previously it only had PM10. Now it also brings fine particles PM2.5, PM10 as inhalable particles, nitrogen dioxide and ozone. So how we can have an overview now. So the microclimatic requirements, we will go this like this, and these are different guidelines coming at different times. So 2008, 2008, 2006, 2010, and then we are here. So guideline values have been done in 2008. This is for worker security. Then 2006 and 2010, which were international values related to chemical pollution for ambient air and indoor air. Then microclimatic requirements were also introduced around 95, which was limited to certain functional units only. Then again 95 and 95. So these temperature and relative humidity norms and guidelines were introduced very early with respect to which kind of room or which kind of activity we are expecting in a room, and accordingly temperature and relative humidity were given. Then ventilation requirements were also given first in terms of the external airflow rate and filter efficiency during the mid 1990s and up to before around 2000. And these requirements were also more limited to like specific units, but by 2008 this association of engineers, they then released the guidelines covering external flow rate, filter efficiencies and even the pressure, and across several units of a house or of an indoor environment. Very recently, monitoring strategies guidelines have also been introduced. For example, sampling methods, but these are any references related to a hospital environment. So if we want to study an hospital environment, what monitoring strategies we need, what would be the sampling method used, what would be the sampling volume that is needed to be collected or passed through, what will be the duration and frequency of this monitoring, and what is about the localization of the sampler itself. So there is some evolution going on. Early evolution or early information came very much in the mid 90s. Then there was almost maybe a lot of gap, 10 years or so. Then a next chunk came between 2008 and 2010, and maybe more recently we have hospitals being included. There are air quality guidelines given by various agencies. The one that we have right now in front of us is the World Health Organization Air Quality Guidelines for the year 2021. So on the first column we have the pollutant. Then on the second column we have the average concentration that is allowed over a given period. For example, annual mean means on an annual average the PM 2.5 concentration should not increase 5 microgram per meter cube. But when we look at a 24-hour mean, which is over a 24-hour period, the PM 2.5 concentration should not increase more than 15 microgram per meter cube. There is a bit more relaxation on PM10 in that the concentration should be 15 microgram per meter cube as an annual mean, but 45 microgram per meter cube, so 3 times basically for a 24-hour mean. So here 5 to 15, here 15 to 45. For carbon monoxide there is only one 8-hour mean value given, which is 4 microgram per meter cube. For nitrogen dioxide there is an annual mean that is stipulated of 10 microgram per meter cube. For sulfur dioxide there is a 24-hour mean of 40 microgram per meter cube as the air quality guideline. For ozone there is a 8-hour mean of 100 microgram per meter cube and a much lower value as an annual mean for lead of 0.5 microgram per meter cube. Now for substance, certain substance there are even more guidelines. So for example, the pollutants which are organic compounds, but other for effects other than cancer or odor annoyance, we have carbon disulfide. For a 24-hour duration exposure, the time weighted average should not exceed 100 microgram per meter cube. For dichloroethane the value is much lower, 0.7 microgram per meter cube over 24 hours. For formaldehyde, the value is high, 100 or higher than dichloroethane of 100 microgram per meter cube, but the duration of exposure, even 30 minutes is deemed quite a lot. So not more than 30. So for a 30-minute exposure duration, the time weighted average should not be more than 100 microgram per meter cube. For methylene chloride, the 24-hour average 3 micrograms per meter cube. For styrene, a 24-hour average of 800 micrograms per meter cube. Some more compounds: tetrachloroethylene, 24-hour average 5 micrograms per meter cube. Toluene, 24 hours average 8 micrograms per meter cube. Then trichloroethylene for a 24-hour average 1 microgram per meter cube. For carbon monoxide, the 15-minute duration of exposure, the time weighted average allowable is 100 micrograms per meter cube. For 30-minute exposure, 60 micrograms per meter cube. For 1 hour exposure, 30 micrograms per meter cube. For 8 hours exposure, 10 micrograms per meter cube. So as the duration of exposure is allowed to be more, the average limit value is also going down. Then hydrogen sulfide for 24 hours, 150 micrograms per meter cube. For inorganic pollutants, the scales are a bit longer. For lead, for 1 year exposure, 0.5 to 1.0 micrograms per meter cube. For manganese, for 1 hour exposure, 1 microgram per meter cube. For mercury, 1 hour exposure, 1 microgram per meter cube. For nitrogen dioxide, for 1 hour exposure, 400 micrograms per meter cube. For 24 hours exposure, 150 micrograms per meter cube. Now, for substances such as mercury, although 1 microgram looks like a small number, the ambient values, the ambient mercury concentrations are actually in nanograms per meter cube. So the actual ambient values are quite low. So 1 is a very high number. 1 microgram is actually quite a high number for mercury. So although the magnitude looks small in itself, actually it may be a large magnitude. For ozone, for 1 hour exposure duration, the time weighted average is 150 to 200 micrograms per meter cube. For 8 hours, it is 10 to 120 micrograms per meter cube. For a 10-minute duration of exposure, the allowable value is 500 micrograms per meter cube for sulfur dioxide. For 1 hour, it is 350 micrograms per meter cube. For the 24-hour duration of exposure, for vanadium, the time weighted average is 1 microgram per meter cube. Now there are carcinogenic risks also estimated for human studies. So there are basically a list of pollutants, and we have a unit risk, which is the cancer risk estimates for lifetime exposure to a concentration of 1 microgram per meter cube. So for acetonitrile, with lung being the site of tumor, the risk is 2 into 10 to the power minus 5. This risk increases substantially for arsenic, 1.5 10 to the power minus 3, so almost 100 times higher risk. And the site of tumor is lung. For benzene, the site of tumor is blood, and the cancer risk is, or the carcinogenic risk is 6 into 10 to the power minus 6. For chromium 6, the risk is quite high compared to all the others, only 4 into 10 to the power minus 2. this is almost 1000 times higher than as acrylonitrile and almost 10 times higher than the arsenic. Then nickel compounds, the unit risk is 4 into 10 to the power minus 4. For polycyclic aromatic hydrocarbons such as BAP, benzoalpha-pyrene, the risk is also comparable to chromium 6, 9 into 10 to the power minus 2, the site of tumor being the lung. For refractory ceramic fibers, the risk is 1 to 10 to power minus 6 and the site is lung. For trichloroethylene, 4.3 into 10 to power minus 7. For vinyl chloride, 1 into 10 to the power minus 6. Now radon, as we have seen previously, also is a special case, and there are reference values according to two organizations actually. There is also from US EPA, that's the third one, which is not listed here. The two listed here are European Union, which is the reference is that if the value becomes more than 400 becquerel per meter cube in an existing building or a new construction, quickly the action should be taken to reduce these levels. And this value basically denotes average annual concentration and a certain equivalent dose per year. For World Health Organization, if the value is more than 100, people should try to reduce the level, and if it is more than 400, immediately action should be taken. So in a way it looks to be more stricter, that 400 means immediate action must be taken. There are also acceptable ranges for temperature and relative humidity during summers and winters. For a certain relative humidity, for example, in the US, the allowable latent temperature is 68 to 76. Acceptable range, 68.5 to 76.0 Fahrenheit in winters and 74.0 to 80.0 Fahrenheit in the summers. Similar value is obtained for is basically given for relative humidities of 40%, 68.5 Fahrenheit to 75.5 Fahrenheit, and in summer 73.5 degree Fahrenheit to 79.5 degree Fahrenheit. For relative humidity of 50%, 68.5 degree Fahrenheit to 74.5 degree Fahrenheit, and in summer 73.0 degree Fahrenheit to 79.0 degree Fahrenheit. Then for 60% relative humidity for winters, the all acceptable range is 68.0 degree Fahrenheit to 74.0 degree Fahrenheit, and for summer 72.0 degree Fahrenheit to 78.0 degree Fahrenheit. So as the relative humidity is increasing, the acceptable range is actually decreasing in terms of the temperature. The minimum temperature has decreased, even the maximum has decreased in winters as well as in summers. Now we also have the examples of standards for ventilation rates and CO2. In the US and Europe, with the association ASHRAE, and it gave the guideline in 2007 for teaching facilities, the CO2 limit was given to be 1000 ppm and a ventilation rate of 7 liters per second per person. For Portugal, the CO2 limit was given as 1000 for all types of buildings, and the ventilation rate was asked to be 8.3 liters per second per person in the schools. Now, and we have seen this before in one of our weekly lectures, the ventilation rates per person and air exchange per person that are required to achieve a selected CO2 level has also been given by this association ASHRAE. For 7 years of age, the CO2 generation in milliliter per second per person is around 1.8. So if the CO2 limit is 600 ppm, the ventilation rate should be 9.2 liters per second per pp. But if we relax the allowable CO2 limit to, let us say, 2000, the corresponding ventilation rate decreases from 9.2 liters per second per person to 1.1 liters per second per person. As we go to age 10, the CO2 generation increases to 2.6 milliliter per second per person, and for CO2 allowable limit of 600 ppm, the ventilation rate required is 13.1 liters per second per person. For the same CO2 limit, if the age of the person increases, the ventilation rate required also increases, because the CO2 generation rate has increased. Now, as before, if we allow more CO2 to be built up from 600, if we relax this limit to 2500, the corresponding required ventilation decreases from 13.1 liter per second per person to 1.2 liter per second per person. For a 15-year person, the allowable the recommended ventilation rate for 600 ppm CO2 is 19.7 liter per second per person, decreasing to 1.9 liter per second per person for allowable CO2 limit of 2500 ppm. The highest generation of CO2 is for adults, 4.7 milliliter per second per person. Therefore, correspondingly required ventilation rate is also the highest. For 600 ppm allowable CO2 limit, the corresponding ventilation required rate is 23.6 liters per second per person, decreasing to 2.2 liters per second per person if the CO2 limit allowed is 2500 ppm. Now, there are also guidelines to allow for air exchange needed in numbers per hour. So, if there was, how much, this depends on how much area is available per person. If only 1 meter square available area is there per person and 2.5 meter cube per person, then basically the person is getting a very confined area. 1 meter per 1 meter is not a lot of area. And to maintain a good CO2 or a better CO2 limit, 600 ppm, the air exchange needs are 34 per hour. So, the air should be exchanged 34 times in 60 minutes, which means once every less than 2 minutes, the whole air should be flushed in this 1 meter square. But if we allow more CO2, then we can have 3 air exchanges per hour. If we increase the available area per adult from 1 to 40 and the volume per adult from 40 to 100, basically allowing for basically a 2.5 meter height, the allowable CO2 limit for 600 ppm allowable CO2 limit, only 0.85 air exchanges per person, air exchanges are needed per hour. And if the CO2 limit is now relaxed to 2500 ppm, only 0.08 air exchanges are needed per hour. So, as we have more and more area available per person, the amount of air exchange required in the room or in the indoor setting also decreases quite a lot. Now, there are some regulatory bodies in India that are establishing and overseeing the indoor air quality standards. One is the Central Pollution Control Board, CPCB, which is a statutory organization under the Ministry of Environment, Forest and Climate Change. The CPCB formulates policies and standards for indoor air quality and monitors the air quality across the country. Then we also have the Bureau of Indian Standards BIS, which is responsible for setting standards and certifying products. The BIS has also introduced guidelines for several indoor air quality parameters. Then we have the National Building Code NBC, which is actually administered by the Bureau of Indian Standards BIS. It basically focuses on the building design and construction aspects. It also includes indoor air quality standards for different types of buildings. Finally, we also have the State Pollution Control Boards, which actually comes under you can say state, but also the state arm of the CPCB. So each state in India has its own SPCB, State Pollution Control Board, responsible for implementing and enforcing indoor air quality standards at the state level. So in summary, we can say there are several regulatory bodies and there are also guidelines or reference values for various pollutants. And we have also some recommended design conditions defined by different authorities. For example, how much air exchanges are needed per hour, or how much ventilation rate is needed in liters per second per person. So this concludes this particular lecture.